Hello, viewers. There's enough new stuff that's turned up that it was worth making a full rerun of all the geometry, just the geometry. And then, of course, as a result of doing that, I found out a lot of other things. So let's go through it all again. About 6 years ago, I believe, Alan Green discovered this geometry, which is defined by these two dots, the G dot and the imprinted dot up here. And this circle will derive both these horizontal I'm anonymous rules that are on this page. And in turn, the lower rule will define a square, and lots of interesting things happen in that square. So we've got a circle that generates a square. Now, it's important to point out that there are only two input points to my model. Right, so all the lines that I'm going to show you, I'm going to say they're exact and perfect because they are. Right, well, what we have to check is how close they are to what's on the page, but the lines themselves are all machine generated, and so in principle, the only two input points are those two, right, and they will generate all of that. Now, I realise that's rather scary. It's really just all of that stuff and a couple of others merged together, and I will be going through all that, of course. Now, when I said in principle, of course, I was lying. While it's been discovered that this circle derives the height on the page of this lower rule perfectly, it doesn't quite define the width of it and the position of it. The position and the width are both out a teeny bit. So you have to give me the x-coordinate of this line that goes through this flower and that flower. And if you do that, then that is it. Those are the only references from the page that are required. So those 2 points there. Right, now there are 5 other variables that are integer degrees, integer angles, and the first is that one, which is the slope of a particular building in Egypt, which is exactly 51 degrees. Well, it's not exactly 51 degrees, that's the point, but we can't measure arbitrary angles. We won't know if we've got something that's worth investigating if it's just and in any case it will inevitably be wrong. You can't do a precise angle on your 16:9 page the size of a paperback. Now, on top of that, there's 4 other astronomical observations which turn up on this page, which I'll explain shortly. And again, they are integer degrees, which in each of those cases, of course, I've looked up, what the declination of Kepler's supernova was, and or still is. It's still out there. So there. So let's get on with this geometry. And we've said these 2 points here, the G dot and the imprinted dot, define 3 circles, this red, green, and yellow circle, which denotes pi, Pythagoras, and phi. Right. So, and if you look at the imprinted dot, it's got this what looks like a triangle on the top to me. And just for reference, that G is exactly sloping at 21 degrees, and we'll come back to that a little bit later. So let's have a look at our first triangle. So this is pi, and it is such that if you take the small side as the diameter of a circle, the circumference of that circle will be the long side, which means you can kind of roll it down the hill and it'll turn 360 degrees. Now, this is what we're talking about in terms of that's exactly where a pi triangle would be based on where the G and the imprinted dot are. We're out tangentially a little bit in terms of I argue that you want a point within a full stop's worth on the end of that line, so round about here, I guess. So we're a bit out, but that's the kind of thing that you just don't notice unless you sort of get down to pixel level. Then the next one is Pythagoras, and that's because it's got sides which have a ratio of 3, 4, and 5, which is a nice, easy to get your head around triangle to choose. Unfortunately, our dot here, the Aspley dot, is anomalous. It's not really where it needs to be. But again, if we kind of stick a triangle on the top, then the point of that, the apex of that, is remarkably close to our circle. We're still out tangentially a little bit. So you can argue the toss about whether or not that's a 3, 4, 5 triangle, but well, I think it is. And then the third triangle is the phi triangle, and that is such that the short yellow side forms a golden ratio with the short green side. So what that kind of means, if you're trying to find a geometric reasoning for that, is that if we put a pentagram on there, then the short yellow side is that length, and we're going to be playing with pentagrams in a short while. Now, there's another issue here, that this 9 dot, right? So this 9 dot is where this triangle, that's the right angle of this yellow triangle, is supposed to be. It's quite a way out. It's half its distance out. Now, it turns out that 9 dot is perfectly in line with this eye, with the inside of this eye. So it's been suspected for a while that this has some purpose and that it's lined up with the square. Well, if I apply a shift and scaling factor between my very short differences between what the circle says the square should be and what the square actually is, I will correctly identify this, and there is a derived point from here which is pixel perfect, which I'll show you. All right, now finally, we've got a couple of construction lines here. The red line across the top, and then across the bottom that goes through those full stops quite nicely. And then this green line from the end of the phi to the corner of the phi to the corner of the pi triangle, and they slice straight through this full stop rather nicely, and that's part of the phi triangle, and as you can see, it runs very nicely along the side of that T. Now, we then have two construction lines, a pair of them. The one from the G is a tangent, it's perpendicular to this diameter, and this one is parallel to it. So the upper one defines the upper rule, because this upper rule is horizontal and it starts from the corner of the pi triangle, and we're going to terminate it here. Now, you'll notice that we start off, that's where our pi one's defined. We probably want it down there, but we're inside the line. But by the time we get to the other end, it's floated up a little bit. Now, this purple line is the line. It's the line that's drawn on the page here. Is the parallel line to this tangent, which then is terminated by the horizontal line coming from the pi triangle, right? It sort of misses this this dot here, but if I draw another line from where this actually is, from that blob at the end of that line to the 9 dot, it will go precisely through there. So I know that the A is lined up with what's on the page, not this derived point. Now, the lower rule is such that where this yellow line, which is the line from the 3, 4, 5 Pythagoras triangle through this intersection of the green and the red, where that intersects this tangent is going to be the left side of this rule, and it's going to go horizontally across and stop at the circle. So the blue stuff is what this circle is deriving as the length and the position of the square. And those red lines are telling us where it actually is, because it is. This has been built from the top down, so it's the value at the top is how all this was placed. So, in essence, to get the red square, to get the square to behave as the circle wants, I have to shift it to the left about 5 pixels, and then I have to expand the whole thing a further 12 pixels in total in order to get this red right over there. And I can that's what I can invert in order to move this 9 dot back into the square frame of reference. So yeah, so there it is, and that's the image that was taken from. So 0.8 of a millimeter at one end, and then it's a total of 2 millimeters, which is 0.8 plus 1.2 millimeters. Now, you may also have wondered why it says at London. Well, it means Aleph Tav, and that's in Greek translates to Alpha Omega. The first and last letters of the Hebrew alphabet are Aleph and Tav, and Omega is the last letter of the Greek alphabet, and we've got the beginning and end construction lines, and I just like that and keep that in. So there's our square. And it goes through the S's at either end, and so it's like, we've got an S in the middle as well. So, and it turns out that an exact center line on that square will go straight to that 6, straight to the 0. The hole within that 6 with remarkable accuracy. That 6 is perfectly aligned to the square. So we want to know where to truncate this somewhere in that girl's face, probably. And it is noted that, a 30-degree line from here will go through the rabbit's eye. So maybe, it's these two, but it's floating in the air. These two triangles are floating in the air. These are obviously two equilateral triangles. So what defines how high up the square they go? And it turns out that there's a pyramid there. If you put a perfect 51-degree pyramid there, in which to balance the two triangles on, you get exactly the right result. And the slope of Giza's Great Pyramid of Giza is 51 degrees and 50 minutes and 40 seconds. So using this concept, they've no decimal point, right? We haven't invented the decimal point yet. Fractions are viewed as this extra bit. So it's quite natural for them to just go 51 and not go, well, that's nearer 52. They wouldn't have done that. And so you can see that this is absolutely bang on this foot. Now that I've worked out exactly where this square is supposed to be. So yeah, 51 degrees, and 51 has quite a bit of hermetic value. Obviously, the factors of 51 are 17 and 3. 17 is part of 1740, which is the two code numbers of our suspected author, and 3 is obviously immense religious significance. There's further hermetic value of 17 and 3. It's the initials of Ray Charles in gematria. But it could also mean the Rosicrucians, perhaps. Now, just for a little bit of fun, I've got two extra triangles here. These aren't part of the geometry, but I've just written a 45 degree and 90 degree isosceles triangle below Khufu's pyramid, and then a 60 degree triangle above it, because I want to put in the top of the full stop on imprinted, and so if you look, we're clearly bigger than the small triangle, nowhere near as big as the big triangle, but we seem to be fitting the mummy triangle, don't we? And that's exactly the same for the stuff on the Aspley dots. Yeah, it's a bit faded on one end, but these two sides do seem to be sloping more than 45 degrees and less than 60. So, uh, so that's good. Now, so we've got this triangle here. We've got the two triangles, so we want a third triangle. We want three of everything. And so now we've got this cross bar here, if you like. That then we can hang an equilateral triangle from there, and it will go through all of the S's, all through the centre of all of these S's, of the 5 S's, which is nice. It will also go through this dot on above imprinted, which we'll come to later. And I'd like to bring your attention to these signatures after the S, which I call the Bluetooth logo at the moment. I don't know what they mean, but it's got 3 triangles, and we're covered in Masonic references. So maybe it's something Masonic. Now, one of the kind of criticisms of this, of what I've been doing, is that, well, it's just symmetrical. All these things happen. I'm afraid they don't. If you want big, thick lines, then you might be able to get something to work. But you can't do the approach that I've been taking and find this on anywhere that it hasn't been put. This is a clone of that page. It's quite useful because it shows us which bits John Wright was aware of, even if you didn't know what they meant. He's copied various anomalies, various typesetting sins, but none of the geometry that we want will turn up. What he's done here is he's turned this this funny full stop into a much bigger one, and then he centered the whole thing on there, and that's blown it. But even if he hadn't done that, these are not the right size to fit with an equilateral triangle. Yeah, if I center them, then obviously a triangle is going to fit. I need a 60-degree triangle, right? And I need things to be well within a millimeter of where they're supposed to be going. Right, so let's do some pentagrams now. We've got 3 triangles. Let's have 3 pentagrams. And so this is the first one, the Great Pentagram, which is defined as having the width of the square and being inverted and symmetrical, on having its bottom vertex on the bottom of the square. And whoopee, in the A, we get... we go straight to, by my calculations now, we're actually going up the inside of this A, and up the rather than through it, which is relevant to some other stuff. But essentially, we've got a golden triangle for an A, which is hit perfectly by that thing, and it also touches this R here. Now, other than that, there's not a lot more else going for that. Just to focus on these A's here. So we have 2 A's at the top, and this one in particular has been adorned, and there's going to be something happening with that one later. So I just wanted to highlight this Thorpe dot has got a kind of a Dad's Army arrow on its full stop. And if I draw a line exactly 30 degrees, it will point exactly at this kink here where this has obviously been added. to the A. You don't really have an A like that. That A is supposed to look a bit like that, I think. So what's going on? We've also got that. I don't know what that is, but one thing I can tell you is it's not SP. That's the only thing it's not. I don't know what's going on there. But if we just look to the top of the page here, we've got alleged A's here with a line across the A at the top of here. But they're not very clear. But if you kind of stick these A's in there, and in fact, if you put that in there, the swoop of that is fitting with the artwork nicely. So I don't know what double A stands for. Aristocrats Anonymous would fit. There are Messrs. War and Shakespeare have mentioned these. They appear on quite a number of the related artworks, but they're there. Right, so then we've got a medium pentagram, but just before we do that, I just want to point out that large triangle there, the Great Triangle, all right, if you follow the 30-degree line down along its left-hand side, it will go straight through this this dot here and hit the A, as we've just done. It's actually about 1 millimetre parallel to the line that I drew you, and I haven't put this on the geometry as yet, but principally because I've nowhere to stop it. I like to be able to put these lines on and truncate them rather than just disappear off the side of the page. I mean, I can stop it on the circle, but that's not, I'd like to stop it on the A, but I don't know. There's no other known geometry as such within that. Although I await to be corrected. Now, so let's get on with this medium-sized pentagram, and this is defined as having that vertex on the intersection of those two blue lines, and that it is defined. I know that points out, but actually that's just a graphics package. The end of that precise end of that pentagram is there, and that's how it's defined. It doesn't touch the top. It's very near, but it doesn't actually touch the top. And whilst I haven't done the algebra as yet, I don't think that's a rounding error. It's just very close, but not quite. But you shouldn't pick that. You won't get the right result. You need to pick this. We could make a pentagram that's defined from here and goes to that, but we'll get a line that's a bit too low. So that's good. And then we've got this dot here. What the heck is this here? This dot appears to be in line with that. So it might be a guideline just to tell you that this is in the right place. But why is it there? Why is it so far across? And then we've got the third pentagram, the small pentagram, which is defined as being the right way up, thank goodness. There's nothing wrong with upside down pentagrams in 1609, incidentally. But so it's the right way up and defined as starting from its top apex vertex on halfway along here. And has a length of root 2 minus 1 times the length of the square, which means, in plain English, the length of the small pentagram plus the length of the square is equal to the diagonal of the square. There's the length of the pentagram, there's the length of the square, and there's the length of the diagonal. So, there we go. Now, we've got 3 pentagrams, 3 triangles, I want 3 squares, and those are my 2 other squares. I've got this big blue square, the great square, and these 2 squares. So I need to introduce you to Edward de Vere the 17th, Earl of Oxford, and the family crest, shield, with this star in this corner. Now, and this O in the middle of where that star would be. The O's just offset, actually. Now, the point is here, irrespective of whether or not you want any of this, is that the strike through on Shakespeare's and the strike through on Neue before imprinted are exactly half the width of the square apart. Therefore, two quadrant squares obviously just fit in. They just do. Okay. But it turns out that this letter T is then perfectly placed. Now, this sonnets has been positioned on the center line of that sonnets is below where that point is. You know, if it wasn't, the T would actually be above the those lines. And we like T's now. What we're because we've got a triple T here, right? So this thing, which looks like it might be the Youth Hosteling Association, is actually the symbol of Royal Arch Freemasonry, and this symbol in the middle is the triple tau, right? And we want to see if we can find a triple tau in here. We can find, you know, a T shape that is repeated. Three times, you know, horizontally in each direction and then vertically, and it's like, oh yeah, well maybe maybe it's in there. Now the point about this triple tau is it's claimed to contain the concealed fourth T, the ternary concealing the quaternary, I think it is. And here's our fourth T, which stands for 4T. So that's why this 1740 is such a big deal. Yeah, you'll just have to put up with it. And a face mask, which I do love, is actually the insignia, the badge of a 32nd degree Freemason of Royal Arch Freemasonry, and the keeper of the Royal Secret, apparently, is this little club. No idea what the Royal Secret is, of course, but it might have something to do with this. So yeah, we want to find our 3T cross. Where is it? Well, it's right there, isn't it? So it fits very nicely. The only issue is how long are these T-bars? Now we've got a dot here, which is very nice. Excuse me. And you'll notice that my blue construction lines are absolutely perfectly on it. Now it turns out that dot is a precisely, and this is a precisely line, 15 degrees from this vertex here. And that just means that I can stick a threepenny bit in there. I can stick a dodecagon, not a 12-legged dinosaur, in the middle of there, and I can extend these lines and I can define all of these, and isn't that pretty? And it's certainly the kind of thing that somebody mucking around with the geometry, somebody who's quite famous for their geometry, is likely to do, in my opinion. So if we look at the H here, that's looking pretty good on that side. But on the other side, the R is just insanely good. Look at that again. You know, you can see where the construction line's going. That's why it looks so good. That's why it's chopped in half, and the blue is on that little pointer. So right now, sticking on this R, right. So of course we noted quite some time ago that there's a break in the R. And then it was noted that, well, we're going roughly through the middle here and possibly hitting the eyes of the B somewhere. Well, if we have a look at this B, it's got a very square top serif, and it's got this kind of stubbed out one at the bottom, which is very suspicious. Now, of course, it turns out that if you draw a 30-degree line exactly from this point, right, if you down and cut it off by the line that goes through all the full stops, right through the middle of the full stops, which we've already got, then we end up right there, right in the middle of this this blob, arguably, or certainly, well, on the line of that. I don't know if that's supposed to be a semicircle or something, or what's going on. But that's a pretty good hit. and then at the other side, right, this then, and I'll do that again. It's how accurate it is for that. Yeah, we end up with at this point, and it turns out, and I'll show you later, that when you reflect that point about this red line, you end up bang on this what is now suspicious dot at the bottom. So isn't that good? So, right, now this right side has got this T that's been adorned. It's got these diagonals cutting the cerise, which is a signal that has been used on a number of places, particularly on the bottom here. We'll go through that in a bit more detail. So, and it was noted several months ago that this 9 dot is in fact lined up perfectly underneath this eye. So we want to try and find a tau cross. Now, so yeah, there's the two, and some kind of gamma thing. I don't know what that's about, but I'm more bothered about this. That is, and this is perfectly centered. And as you can see, that's the center of the square. But the line that we're going to be using, the line that we use, the pink line, is there, which is below it, not the same. Right now, we're going to use this line here, right, and we're going to derive it by taking the x-coordinate of the phi triangle and shifting and scaling it by the 5 pixels and then half of the 11 pixels, in order to move it about 1.5 millimeters. So I'll say 1.5 there. So that's that. I'll just explain that. The yellow one is in the wrong place, and so we need to do the shift and scale. And so the point about that is that will make the length of this side of it twice as big. Right now, this is defined. I didn't say that. This is defined as the left side of this is from the midpoint, the midline of this square. Right, so that doesn't change. I've just moved the pink line, the vertical line, to the right 1.5 millimeters, and that means this is that much bigger. Right, but that also means then that this is that much bigger as well. So we're a total of 3 millimeters, which is quite a distance on here, away, the size of a decent full stop. I'll be able to notice it. And here we've got this dot, and I swear to you, when I first created this tau cross, I hadn't even seen it. So I was ignoring things of this magnitude. Now I've been drawing the line just a bit above this, but it's been bang on. We've had the width of this perfectly. It's just that I've recently realised that we were drawing the square about 5 pixels too high, 6 pixels too high. And yeah, that's where we end up. That's where the pink line ends up. So I've just done that now twice. Right, we got the R, and now this dot, right, which are precise. So I now know that I've got the dimensions and the locations of the square absolutely perfectly. And a bunch of other stuff started to click into place as a result. So, yeah. The bottom of these two squares goes straight through Neue before imprinted, which, as you can see, has got quite a lot going on it, including a scar that I put on my version, which I'm keeping there for now, because completely accidentally. I mean, I was rubbing out these lines down here so that I could put just a thick black one in its place because it was confusing. And that point here, I think it's actually really geometrically where the reds connect, but the blue point is the medium-sized pentagram. And there's a lot going on ore, and I've heard people talk about ore in cryptographic circles. And you can see here the eye, how that goes up the inside and doesn't go through the eye, but it goes right along, the side of it, which is pretty good. And you can see this strange thing here being beheaded. So yeah, we go straight through the E's, and I don't know whether or not the E's, whether or not this E in particular, this penultimate one, is a dolphin. This sturgeon-like thing is an heraldic dolphin from the era, I think. I mean, next to it, I don't know what that could be. A whale. This is a fish finger. This is a couple of triangles, but at least there is something going on. We've got three more E's in R, and then to be sold, and the first one is a larger font size than the font size of Neue before, and it has a filled-in E, I of the E, as did these two. I wonder whether or not this had a mouth on it or something. This one is now starting to look like it's got a tail and a fish's head. But that's really where I am at the moment. We need as high a resolution as we can get our hands on. So we've done with the square, and we get down to let's go back to the circle, because we've now got three exotic crosses. We've got our Tau cross, fantastically corroborated here. We've got this big green cross, which I'm hoping to turn into a rosy cross at some stage, but it's a big green cross with lots of geometric significance. And then we've got this yellow cross, right, which is defined as going from the 9 dot through the center of this circle, and I'll mention this X in a minute, and up, and then is truncated at the same point as where the pentagram terminates on the A. This X here, this chi, is created by reflecting this initial diameter about the X or Y axis, so that this coordinate has got the X of this and the Y of that, and this has got the X of that and the Y of this, and this lands on that's U for a V perfectly. So, and this has got a little bit of cryptography, by God, and this cross in the middle can be an and sign, can't it? By God, and DE, VE, RE. So I just wanted to give you some kind of weight on why have you created that X? I mean, obviously that's fairly significant, but and that message is repeated on the next page twice. Right, so let's just have a look at this line then that goes through it, and first of all, the line from the 9 dot, and it's from this point, not that point. It's from the phi triangle. You'll miss if you go from the other one. This line is to do with the circle. It's all to do with the circle. So we go from where the circle says the 9 dot is, and we go through the precise center of this circle, and we will hit the center of this what I suspect has actually got an ossuary on the bottom, but the center of this full stop, either rather perfectly, and then run up here. Now the thing is, as I say, we're not going to do this shifting. We're going to keep that, but the P is obviously in the square frame of reference, so we need to invert this 1.5 move because we're roughly at the same distance across the page, so the scaling will be the same. And so we want to move that P 1.5 millimeters, and if we do that, then that yellow line is going to be right up the inside of the P, which is where I would expect it. It's where the pink line goes through the I. It's where the green line goes through the N. Right. So that might seem a little bit acute, but we have to get down to this kind of level of accuracy now. So what's next? Well, I quite like a star chart to turn up, please. So this is the Rosicrucian Manifesto from 1618, and on it has clearly got Kepler's supernova of 1604, because it says 1604, and it's got a bloke on a scrap with a snake, and I can't remember the name of the constellation, but it's a bloke scrapping with a snake, and that's Kepler's supernova, and Tycho's supernova, and this looks like it might be another one of them, is in the constellation of Cygnus, I believe, and we've got a great big swan, and I don't know what that says upside down, but yeah, these two are the two supernovas. Now, whether or not these flying postcards mean comets is irrelevant, but I think there were 4 comets in this era. But the point about this is that the 3 most significant astronomical events of this era, of the Shakespearean era, are without question these 2 supernovae and the Great Comet. The Great Comet changes things, as do both these supernovae. The supernovas change our view on the inconstancy of the universe, and the Great Comet, before the Great Comet, we're not even sure what comets are. Kepler notices that it actually gets quicker as it gets nearer the sun, and that's rather important for his analysis and explanation of the path of Mars, which will, in 1609, blow the lid off everything. So let's see if we can find these 4, well, there's 3 things, but I'm going to find 4. The 4th is Venus, which is the brightest object in the sky. So, as I say, if you were to ask 100 astronomers for the best 4 things to look for in 1609 that had happened in living memory, it would be these 2 supernova, the comet, and then you might then say, well, Venus is the brightest object in the sky, so we'll have that as the 4th one, which is what we've got. So let's have a look at this. These 4 letters that have all been edited. This is S. The first S has got a dot there, which is obviously halfway across there, and is nicely in the middle of this lower, whatever you call that, the base of these letters. Right, the A has got this bizarre notch on the bottom, and yeah, he's in the corner, so it kind of fits with stuff, but it's nicely on that line again. And then we've got the R, which has got a dot there, which is near as damn it in the middle. But it's also very much along this this footer line thing, and then we've finally got that dot, which admittedly, if you hadn't shown you the previous 3, you might be. It's like, oh, we can't go near there. Look at all this, mottling here, but it is slap bang in the middle, and as such, and it is bigger than the other ones. So there. So these are our 4 dots, right? So let's go through each of them, and this is the first one, and this A. We need to have a little bit of a look at the A, and this strange foot that it's got. This is the left-hand A. If we put 2 transparencies together, you can clearly see that we've got this kind of notch, this kind of foot. right? Now, the G, I innocently measured that to be a little bit over 20 degrees, maybe, before I drew the line up there. But so let's just do it, and we find out that it's at 21 degrees exactly. The measured angle is 21.06. But that's actually that number should come down. It's we're at such accuracy that the granulation of the page of the pixelation is such that 1 pixel difference is changing that. So this line is intended to be 21 degrees. Kepler's supernova is the biggest thing that ever happened. I think it is. I don't know if it's the largest one, but it's certainly. There haven't been that many supernova that have been witnessed in the whole of recorded history. And it turns out that has a declination of 21 degrees. And so I'm going to apply let's just take the degree thing, but I need to have a very nice, very close to 21 degrees line, and that's what I've got. So I'm having Kepler's supernova. And it's just been noted that this G, if you take this 21 degree line and you just move it over here, it just goes straight through there. That G is lined up in order to just nudge you along if you needed a bit of extra help. So that's good. So we've got supernova 1604. What about supernova 1572 then? Could it be there? Well, it's got a measured angle of 63. As I say, I think that's an ossuary. I certainly seem to have some kind of globe maybe there, and I don't know what's there, but it's been mucked around with. Now, the declination of Tycho's supernova, as measured by Tycho Brahe, who was the only person capable of doing anything like that at the time, is 63 and 53 minutes. He actually got it wrong. It's just over 64, but I don't care, because that's anybody making this diagram would use 6353, and so they'd have drawn a line at exactly 63, and this measured angle is 63.02. As I say, I could probably make that a little bit better, which is quite preposterous. So finally then, is this the Great Comet of 1577? And that does look a bit kind of comet-like, and in the circumstances. Now, if we take a line from that very dot and draw it straight to this same point here, it will go straight through our suspected comet. Now, I suggest, so what's the angle? And it's got an angle. Well, I put a measured angle of 21.11. I need to redo this. It's not 19.99. It's a little bit, but it's it'll be 20 and a bit. But that 20.11 is a bit out. I don't like that. I'd rather that to be under a tenth. But if we'll take that as 20 degrees, and we've got the other three, then I am of the opinion that this comet was measured it was witnessed exhibiting an occultation, which I understand is what astronomers call an eclipse, with a object of known declination of 20 degrees, or 20 something up to, but not including 21. So all we need to do is read Tycho Brahe's detailed accounts of this comet, and he'll tell us if on any of the evenings he was watching it that anything interesting happened. The only trouble is that, rather astonishingly, his Latin account of this has never been translated even into Danish. I mean, I've had a historian of astronomy complaining about this. What the hell's going on? This is one of the most influential people in the history of astronomy. This is one of the most important astronomical events. As I say, we the whole comet issue changes after this thing. and yet we can't read it even in Danish. So if someone can go through that and try and work out which planetary heavenly objects that he's making a fuss about, we can check them to see whether or not any of them have got a declination of 20. So now sticking at this R, so this R has got lots of stuff going on. It's got this great pentagram pointing on it. It's got this ore line, as I call it, that ends up on it. It's we've got this red line here, which we need to explain, and I think that is a manicule up here, and that he's pointing down to it, and we've got our tau cross that beautifully is terminated there. So let's just have a look at how we make this this red line here, and we start on this side, and we're going to reflect that at that point about this this tau cross, this triple tau, I beg your pardon, excuse me, and we'll end up right there, which is actually, that it's actually on that dot there, which is actually inside this freckle, which I think is pretty good. Now on the other end, so we're going to draw then at 23 degrees exactly, because that's what it looks like when we measure it. It looks like it's nearly 23. Let's use 23 exactly. And we need to take the baby pentagram, and we're going to reflect that point about the this critical strike through of sonnets in the mummy pentagram, that point is going to be there, and so that's how we're able. Well, it's actually that's a horizontal line that I'm defining. And so if that was a teeny bit lower, we'd actually end up in there. So, but that's not too bad. Certainly the star end of that's not too bad, and we are clearly coming from the middle of that bauble thing. So 23 exactly. What's that then? What has got a declination of 23 and something? Well, this R appears to have a bit of a beak on it, which looks a bit like that, but maybe it's one of them, a peregrine falcon. Now that's a picture of the evening star. I believe it's actually the morning star. There's a Slovenian archaeologist that's been investigating Mayan civilization and their astronomy, and needed to know exactly where Venus was in this time, because the planets move around a little bit over the centuries. But I'm pretty sure it's either the morning or evening star. And of course, Venus is Horus in Egyptian mythology, and of course that's this guy. So my favourite, I think, of Egyptian deities. Now this R here is a bit weird, and this is again where John Wright comes in as rather handy, because he's gone and highlighted this this R for some reason, and in fact, if you look on the Aspley version, you can see actually. So this is why we need even higher res. You can see that we look as though we've mucked around with stuff from here downwards. We've obviously mucked around up here as well. So, but this has been glued on. It looks like he's got two boots. So yeah, I think this foot is way too long. You might have it sticking out a little bit, but that's a significant proportion. It's half as much again. So now, we've got our fantastic little dot here that's got a little point on it. So I'm going to be a bit artistic because I want to do that. Now I'm being a bit cheeky now, sort of getting into Egyptology, but who knows? If someone knows a little bit more about this, they can weave some narrative. So we got 4 of these that are all using the same principle. They're all in these regular, quite similar dots on the night sky of Shakespeare's, all using this rounded degree stuff, where we take the rounded value of the stellar measurement, and so we just take the degree value and then we draw a line that's as close as possible to the integer degree, and that happens 4 times to the 4 arguably most significant events. As I say, if you gave that to 100 astronomers, I suspect that those 4 are going to come out as winners, and certainly in any kind of top grouping. Okay, so there's just a few other bits and pieces here on this. The shake, this S, sorry, is noticeably in the wrong place. That dot should be on the blue line. Why is it moved in so much? I'm confident enough that I know that blue square is down right. So why is that now wrong? Why have they deliberately done that? Now, part of it is just to say, "Oh, look at me! I'm Tycho's supernova." But you could just move it down a bit. Why is it so obvious? And it may be that blue line there in that instance is meant to be interpreted as an eye, so we can have insignal hoc on that side, and then we can have on the other side of the central T of our triple tau, we could have Horus's eye, maybe. I don't know whether or not we should put those up there. They might fit. What I really want is a rose to turn up there. It has to be such that the center of this, the pistil of this Tudor rose, this pentagon, is exactly on there, on that point. But the reason I want it is actually because I want this cross to have more clout. Now we've got 3 pentagrams, obviously, but they're not in the right place. So yeah, you can just plonk them on and go, look, I've got a rosy pentagram, but that's not floating my boat enough. We've got 5 S's, so I don't know if they've got something to do with anything. And then we've got this. And the point about this is that it's a funny mark, and we'll need to decide whether or not it's Homer Simpson or not. But it's perfectly on the on this geometry. It's perfectly on that great triangle, and that's quite something. It looks at that resolution. It looks really quite suspicious, doesn't it? So why are we doing this? Why did whoever made this do this? On the next page, it says quite clearly, to the Westminster at South Transept St. Peter's, De Vere lies here. And that solution is in a completely different order of magnitude to almost everything else I've seen in the cryptography. I could put a presentation together at this stage on rubbish that I've seen, right? Because there's loads of bogus stuff floating around, and this kind of creates this fog, right? The Cardano on the next page has been clunked from Kennington to St John's Wood, right? And it's astonishing to anybody who's bothered to look at it why it's not been accepted. So we've been told to go there, and yeah, we've actually been told to go to the south transept. So here's the south transept, and there's our circle, and this is the cross. So let's see what that means. So I've put very loosely 5 columns from the south transept on here, and I put this red box, which is actually St Glade's Chapel as then was. Now, and to the left of this, we have D for T, and that T is really weird, isn't it? It could be an ox. It's some kind of bovine thing, isn't it? Sort of, yeah. Well, that obviously. Now he's just mucking around here. I mean, it is a weird T, you got to admit it. But I've seen it twice, and I'd like to find some more. Where you've got Earl of Oxford nicely centred on the page, and then on the same line, further along, you've got Defort. So what? That turns up all the time. I mean, it's minor, no, but when you've got Defort that's been perfectly set above it, and then obfuscated by sort of jiggling stuff around it, so that you can't see it really. But if you just cut out the letters of this, it's set perfectly. That's not normal. So, irrespective of whether or not you want to accept this guy, what works of art this guy wrote, as far as Defort being a known symbol, moniker, even, or whatever, code, you can actually prove that. It turns up that many times. So that very point there was the St Glade's Chapel. We've now got a cross of religious intent on its side, haven't we? And and at that point, that sacred point, is where the altar is of churches. And there's our cross there, isn't that nice? There, that sort of that very point. So, and yeah, that's that point. Which, if we just zoom in on that, when that was built, it had 17 railings around it, and I know he looks like he wants to go for a wee, or maybe he's Knights Templar. Okay, the Freemasons, they've just decided that Shakespeare needs to make a Knights Templar sign for them, but that could also be 4X, maybe. As well as being a Cairo. He's pointing to lots of dodgy stuff. He's pointing to 4 T's that are actually misquoted Shakespeare, and temples and all kinds of stuff. Nothing on this entire thing was done by chance. There are 40 notches across there. There's 17 notches across the top. Anything that they can muck around with, they will, and if they can't, they won't put it in there. And it was put up in 1740, of course, having been bagged 20 years earlier. They came out and became an official public outfit in 1717, did the Masons, and immediately bagged this spot and threw this wall up, which is pretty rubbishy, actually, this wall, and then turned up 20 years later to put this thing there. So there. And then, so finally, we've got this dot there, which I'm taking as a circle, actually. And within this triangle here, we've got D with 2 sacred crosses through it. And it was John D, that could be a delta. John D's signature was delta dot. He used that on quite a number of occasions, I understand it. It's been signed multiple times, signed several times on the other page, and I wouldn't be surprised if we find some more on here. So let's just run through all that. The 3 pillars of geometry, horizontal rule generator, 3 equilateral triangles, three perfect squares, three pentagrams, a dodecagon inside a triple tau with Horus. We've got three pyramids. We've got a star chart, and with the three most notable astronomical events in history, let alone our era. And then we've got all these signatures at the end, and weird A's and delta dots. So there. That has to be enough to make some movement, surely. But you've got to get people to look at it. Now, if you want to play this game at home, folks, I need to warn you that there is a pirate copy on the market, which for the purposes of cryptography is absolutely useless. It's obviously similar, but it's not the same. Now, here's one of my favourite Stratfordian punch bags. Sid Lee, who in 1900, and from his offices in St James's, no less, which, if you didn't know, is the epicentre of the British establishment, in his hackney carriage, it would have taken him approximately 15 minutes to get either up Haymarket and Shaftesbury Avenue or across Trafalgar Square and up St Martin's Lane to Great Russell Street and the British Library, which would have had both of these, and he could have sat there and looked at them with the jeweller's magnifying glass on a angle poise that he's demanded, and have a bloody good look at these for like a minute, Sydney. So let's just have a look at those, and it's ridiculous. I mean, it really is. It's just shameful. There is no way these two are from the same printer's form. If you want to argue that they were both made in 1609, okay, I mean, I can't argue on that, although we can have a look at, I don't know if we can carbon date the paper, it's too near. But there may be other ways that you can actually view the paper, that it's a different style that wasn't being used or what. But these are not the same. And that whilst he's aware of stuff, he doesn't know what it means. I suspect John Wright had noted that the real one is starting to change hands for considerable sums of money for the day. And so he's going to make a pirate copy and bang them out, and no one will know any different. So that's what I think, and I think he made a lot of them as well. But Sid thinks that they're an imprint, and comes out with a pack of rubbish. Now, I've been accused of being dismissive. Nothing that this man says means anything, and the thing is that he's, as I say, he was at the epicentre of the British establishment. This book, the Dictionary of National Biography, he's a core figure. He's the principal figure in creating this, a Wikipedia of Great Britain. And as a noted Shakespearean scholar, and talks absolute rubbish. That I'd expect a child to be able to do this if led. Are these the same? And come up with the answers. So be very careful about using this for cryptographic purposes. None of the geometry works. And I don't believe he's aware of anything else. So if you're going to start bringing his name into it, if you're going to start bringing John Wright into this, I think you might be constructing a counter argument with respect. And as regards the rest of the book, whatever you're looking at, you've got to go back to the Aspley and make sure that it's right. I just throw this in the bin. Stop using it. Use this. It's free. So just thank you again to Green in particular. We would not be looking at this without him. War on a number of levels, and Hall Carpenter is particularly responsible for the triple tau stuff. and was very useful during the surge that we had on this. David Shakespeare, because I spelt your name wrong, mate. Sorry, but also John Anthony and Glenn Alexander, who, as you may gather, I'm trying to keep tabs on now. And I mean, there isn't anything. Well, there isn't. There's something that I disagree with on this subject with everybody on that list, right? So it's not as though I agree with everybody, and I'm sure they don't agree with me. Yeah, it's peer review we need. That's it, really. I'd like to say more news as we get it. I kind of packed in, and then I found a lot of stuff out, such as the G slope, and also the Aspley arrow here and stuff. But principally, what I've just discovered is that we only actually need the x coordinates of these two, because we've actually predicted the circle predicts the height of that perfectly, yeah, I really, 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 really do need a higher resolution version of this from the British Museum, please. Um, More news sometime.